Question, we have a differential equation. It is given, well, these are the initial conditions, y equals 3, when x equals 1. Use Euler's method with a step length of 0.1 to find an approximate value of y when x equals 1.5. Okay, so these are typically worth about 4 points, and if you get the right answer, you get all 4 of those points. But if you want to show a little bit of work, you can show what steps you're typing into your calculator to get a M1 point. So the steps are, like from the formula booklet for Euler's method, xn plus 1 equals the previous x value plus the step value. Okay, and for the next y value, we have the previous y value plus the step size times dy dx. Okay, which is yn plus 0.1 times the dy dx is just this divided by x squared, right? That looks a bit confusing with the x symbol. Let's write it like this: y squared minus 2x squared over x squared. Okay, so that gives you an M1 point. If you get the wrong answer, you still get a point for writing that. The right answer just involves typing into your calculator. Okay, so I'm going to use this HP prime to type it in, and you go to sequence, and this is my settings. Start at n equals 0, and just type in un n minus 1, so that's for the xn, that's the previous x value. And the same thing for the y value, just typing this into this format, right? And you can do a similar thing for other calculators and look it up in the table until you get across from 1.5, and we have the answer is 10.7. In part B, we use this substitution y equals vx to show that this equation is true. So this is using homogeneous equations, and you should know how to do that. It's always the same. First step, dy dx equals v plus x dv dx. And then we do a substitution on this equation here. So we have, let me do it over here on the side. We have dy dx equals y squared minus 2x squared over x squared. So you want to get it in the form of f of y over x. So you want to actually divide both these by x squared. dy dx equals y over x squared minus 2 if we divide by x squared, right? And y over x is simply v, and dy dx equals this. So we have v plus x dv dx equals v squared minus 2, and hence x dv dx equals v squared minus v minus 2. Next, in part C, we have to actually solve the differential equation that we set up from before. So we can separate the variables and start solving. So let's bring the v's to the left and the x to the other side, and we'll have 1 over v squared minus v minus 2 dv equals 1 over x dx. And let's integrate both sides. The right hand side is ln x plus c. Here we have to use partial fractions, so maybe we'll do that on the side. Partial fractions. So that factorizes the denominator into v minus 2, v plus 1, and that equals some constant a over v minus 2 plus a constant b over v plus 1. Okay, and let's solve for the a and the b. So let's multiply both sides of the equation by this whole thing, and we get a times v plus 1 plus b times v minus 2 equals 1. Just 1 on this side, right? So we're going to have an AV and a BV, so we're going to have a plus b v equals a minus 2b, plus equals 1. And there's no v on the right hand side, so that means a plus b has to be equal to 0, and a minus 2b has to be equal to 1 to get a 1 here, right? So solving those, we can subtract these equations, and we get 3b equals -1, b equals -1/3. And that means a plus b equals 0, so a has to be equal to 1/3. So this is the same as the integral of 1/3 over v minus 2 plus -1/3 over v plus 1 dv. And you can factor out the 1/3, and we have the integral of that is going to be, actually, do we need brackets? Yeah, sure. So ln v minus 2, that's going to be a minus. Ln v plus 1 equals ln x plus c. Okay, so we can, maybe the best thing to do is multiply both sides by 3, and then we can combine these using a log rule. Ln v minus 2 over v plus 1 equals 3 ln x. Now 3 times c is just another constant, so we keep that as c. And to solve this, actually let's bring the 3 up here using another log rule. So we have ln x cubed plus c. And then we can do the opposite of ln, which is e to the power of, right? So it's going to be v minus 2 over v plus 1 equals e to the power of ln x cubed plus c. So that's v minus 2 over v plus 1 equals, this is the same as e to the ln x cubed times e to the c. And usually we write that as another constant altogether. Okay, so I guess you can, well, we used a previously, but let's just use this again. So we have that, actually, sorry, e to the ln x cubed is just x cubed, right? All right, at this point we want to change y, or sorry, v back into y over x. Let's do that. Y over x. Let me just rewrite that. Okay. Now we can rearrange. Oh, let's actually do that. That's actually pretty easy. We can multiply numerator and denominator by x here. And we get y minus 2x over y plus x equals ax cubed. And at this point, I guess we can figure out what the a value is, and then we'll solve for y. Remember, our goal is to get this, right? Our initial conditions are x equals 1, y equals 3. So let's sub in x equals 1, y equals 3. And we have 3 minus 2 over 3 plus 1 equals a times 1 cubed. So that's 1 over 4, so 1/4 equals a. So our equation now is y minus 2x over y plus x equals 1/4 a, sorry, 1/4 x cubed. So we want to solve for y, you got to multiply both sides by y plus x, so I have y minus, and actually just multiply by 4 as well to get rid of that. So we have 4y minus 8x equals x cubed times y plus x. So we're going to have 4y minus 8x equals x cubed y plus x to the power of 4. To solve for y, we bring the y's on one side. We have 4y minus x cubed y equals x to the power of 4 plus 8x. Factor out the y. And we have y equals x to the power of 4 plus 8x over 4 minus x cubed. And this next part is asking for the actual value of y when x equals 1.5. Recall earlier we did this with Euler's method, but we can get the exact answer now by just using what we did in this previous part and just substituting it in. Okay, previously we got 10.7. Let's see how close it is. Okay, so just type that into our calculator. Okay, we've got Let's make this a fraction. Okay, everything's typed in correct, and it's 27.3. Okay, so that's not even close to our result from before, actually. Okay, next in this last example, using the graph of this function, which is what we had before, the solution to the differential equation, suggests the reason the approximation given by Euler's method is not a good estimate for the actual value of y, which we calculated here. So if you graph it, let's take a look at the graph. I'll just type it into the calculator. So you can see at x equals 1.5, you can say one or two things to get this is only 1 point in the mark scheme. You can talk about how steep the function is here, or the fact that there's an asymptote nearer 1.5, right? Okay, and there's only one pointer, so you just need to say something like that the graph is very steep. The graph is very steep around x equals 1.5. Maybe you could even say and there's an asymptote, or because there's an asymptote. There's an asymptote. Let's say vertical asymptote, just to be clear. The vertical asymptote's at cube root of 4, which is actually pretty close to 1.5. That's why we get it there, right? So that's enough to get you the point, but let me just explain it a bit clearer. So the graph looks like that and like this. Okay, so the way the Euler's method works is like going from the origin from x equals 0. Actually, we're starting with x equals 1 in our Euler's method. So x equals 1. Let's draw that a little bit more accurate, actually. At x equals 1, it's very steep. So the way Euler's method works is you just make it like a tangent line, and you predict where the next point's going to be, and then you use the slope there to get another tangent line, and then you predict where the point's going to be, and then you do that again. So it gets pretty wide pretty quickly. If the graph is increasing very quickly, then it can be a problem with Euler's method, because this distance here is the actual value, right? So it gets very, very high very quickly.